Dear students, I am Hiba Haq, lecturer of physics from Government Degree College, Malir, Cantt, Karachi. This lecture is about standing wave, which is a topic from chapter number 8, first year Sen textbook. I have divided my lecture into 4 portions. First of all, I will explain what are transverse standing waves. After that, I will drive an equation for standing waves and identify the location of nodes and antinodes. After that, I will explain fundamental frequency and harmonics and drive their relevant expression. And in the end, I will explain sonometer and drive its expression. Transverse standing wave. In my previous lecture, I have explained transverse traveling wave. In this lecture, I will focus on standing waves. Standing waves is a combination of two waves of equal amplitude and frequency moving along the string in opposite direction. The phenomena is the result of interference, that is when waves are superimposed, either their energies are added together or cancel out. Or we can define standing waves in another way, that two identical waves having same amplitude and frequency moving in opposite direction overlap with each other to form standing wave. So standing wave is actually the interference of two waves or two identical waves. By identical we means that they have same frequency and amplitude, and they are moving in opposite direction, which means that they are out of phase with each other. So the first wave is the incident wave and the second one is the reflecting wave. So here is a diagram in which we have a string and wave is propagating through the material medium, which is a string, and the one end of a string is fixed while the other end is free. So when the wave is traveling, this is an incident wave, and when it strikes with this, it will bounce back. So it will become a reflecting wave, and when these two waves overlap, either their energies are added or cancel out. Now I'm going to drive the expression representing the equation of standing wave. For that, I'm considering two sinusoidal waves with same amplitude, frequency and wavelength, but traveling in opposite direction, which means that they are out of phase. These waves can be written as y1 xt a naught sine kx minus omega t. Second one is y2 xt a naught sine of kx plus omega t, where a naught is the amplitude, omega is the angular frequency, and k is the wave number. So this positive sign and this negative sign, difference in sign, shows that the both waves are out of phase. Y1 xt represents displacement of wave traveling to the right, taken as our incident wave, and y2 xt represents displacement of wave traveling to the left, which is our reflected wave. Wave numbers are the ratio of 2 pi upon lambda, or omega is the angular frequency, where lambda is the wavelength of the wave. Okay, so here we have a diagram in which the dark line shows the incident wave, where dotted line shows the reflected wave, and the wavelength is the distance between a crust or a trough. I have already explained you what is crust, what is trough, and what is wavelength in my previous lecture. Crust are the point on wave where the displacement is at its maximum, which is this, and trough is a point on wave where the displacement is at its minimum, so which is this point. And wavelength is the distance between crust and trough, or between two consecutive crust or two consecutive trough. So let's suppose the length of the string is L and wavelength is lambda. So when these two waves superimpose or overlap, the resultant wave function y of xt is given as y1 xt plus y2 xt. So we just add the displacement of the incident wave and the reflected wave. So putting the value of y1 xt and y2 xt, y xt become a naught sine of kx minus omega t plus a naught sine of kx plus omega t. So if we take a naught common, y of xt is equals to a naught bracket sine of kx minus omega t plus sine of kx plus omega t. So this expression or this is similar to a trigonometric formula, which is sine a plus sine b, and we know that sine a plus sine b is equal to 2 sine a plus b upon 2 into cos a minus b upon 2. So here a is equal to kx minus omega t and b is equal to kx plus omega t. So we expand this term using this formula. Y of xt is equals to a naught into bracket 2 sine kx minus omega t plus kx plus omega t upon 2, which is a plus b upon 2, into cos kx minus omega t minus kx minus omega t. So if we multiply negative with this bracket, minus plus minus minus plus minus, so this is a minus b upon 2. Or we can further write it as this omega t will cancel, and this kx will cancel. Y of xt is equal to 2 a naught bracket sine 2 kx upon 2 into cos minus 2 omega t upon 2. So this 2 and this 2 will cancel, this 2 will cancel. Final expression will be y of xt is equals to 2 a naught sine kx into cos of minus omega t. And we know that cos of minus theta is equal to cos of theta. So y of xt is equal to 2 a naught sine kx into cos omega t. This expression represents the wave function of a standing wave. Now using this expression, we try to locate the nodes and antinodes. So in this expression, amplitude is 2a sine kx and angular frequency is omega. We know that it is equal to 2 pi f, and wave number is k is equals to 2 pi upon lambda. Okay, maximum displacement, which is antinodes, the point located on the wave where displacement is at its maximum is called as antinodes. For locating at the points on wave that represent maximum displacement, we assume that sine kx is equal to 1. So we all know that sine theta or cos theta are periodic functions, and they repeat their values after 2 pi radian or 360 degree. If we talk about sine theta is maximum when angle is 90 degree, or if you talk about radian scale, it is pi by 2 radian, and its value is 0 at 0 degree or 0 radian. So for maximum displacement, sine kx should be equal to 1, and we can say that kx is equal to sine inverse 1, and sine inverse 1, value of sine inverse 1, value of sine theta 1 is at pi by 2, 3 pi by 2, 5 pi by 2, up to so on, and generally we can write it as n plus half pi, where n is 0, 1, 2, 3, so on. Okay, now the first antinode will be at pi by 2. So kx is equal to pi by 2, where k is 2 pi upon lambda. So 2 pi upon lambda x is equals to pi by 2. So this pi and this pi will cancel. X will be equal to lambda by 4. So the first antinode we get is at lambda by 4. Now if we talk about second antinode, it will be at 3 pi by 2, or again kx is equals to 3 pi by 2, where k is 2 pi upon lambda. 2 pi upon lambda x is equals to 3 pi by 2. Again pi and pi cancel, so we get x is equals to 3 lambda by 4. And the third antinode will be at 5 pi by 2. So 2 pi upon lambda x is equals to 5 pi by 2, or we can write it as 5 upon 4 lambda. So in general we can say that 2 pi upon lambda x is equal to n plus half pi, or we can write it as x is equals to n plus half pi, pi cancel, so it is lambda by 2. Now let's talk about nodes or minimum displacement. The point on wave where the displacement is at its minimum, which is 0, is called as nodes. For locating the points of wave that represent minimum displacement, we assume that sine kx is equal to 0, and for that kx is equal to sine inverse of 0, and the value of sine inverse 0 is at kx is equals to 0, then pi, then 2 pi, 3 pi, up to m pi, where m is 0, 1, 2, 3, up to so on. So first note, sine 0 sine theta is equal to 0 at 0 radian. So kx is equal to 0, 2 pi upon lambda x is equal to 0, or x is equal to 0. Second note, when sine theta is at pi, so 2 pi upon lambda x is equal to pi, pi cancel, we get x is equal to lambda by 2. Then we have third note, when we have angle 2 pi, so sine 2 pi upon lambda x is equal to 2 pi, 2 pi cancel, x is equal to lambda, or in general we can write it as 2 pi upon lambda x is equal to m pi, or x is equals to m lambda by 2, where pi cancel. So these are the general formula in which you can put the value of n, m, which is 0, 1, 2, 3 up to so on, and easily find the location of the points where displacement is 0. So here is a diagram which represents the location of nodes and antinodes. So if we talk about nodes, we have nodes at 0, then we have half pi, half lambda, then we have lambda, then we have 3 lambda by 2, and then we have 2 lambda, and so on. And if we talk about antinodes, we have lambda by 4, which is half of the half wavelength, then we have 3 lambda by 4, then we have 5 lambda by 4, 7 lambda by 4, and so on. So these are the points where the displacement is at its maximum or at its minimum. Now let's talk about fundamental frequency and harmonic, one of the most important topics of this chapter. So we are going to drive the expression for fundamental frequency and harmonic. So for that we consider a string of length L fixed at both ends. Standing waves are set up by continuous superposition of incident and reflected wave from the end. The string has number of natural pattern of vibration, we called it normal modes. So here we have the modes of vibration. So the first one is that when a string is vibrating in one loop, then when a string is vibrating in two loops, so this is the called as one loop, which is that from node to the consecutive node. So this is one loop. And then we have a string vibrating in two loops, then we have a string vibrating in three loops, four loops, up to so on. So we are going to drive the expression for the frequency of individual modes of vibration. So okay, first harmonic or fundamental frequency. If the string is plucked from the center, it generates single or one loop. The length between two consecutive nodes or the length of one loop is equal to lambda by 2. You just remember that length of one loop is lambda by 2. So this will help you in solving the numericals. Now since we are talking about first harmonic, so L will be equal to lambda 1 upon 2, and lambda 1 will be equal to 2L. Now we know that the product of frequency and wavelength is equal to speed. So for first harmonic, f1 lambda 1 is equal to v, or f1 will be equal to v upon lambda 1. Now put the value of lambda 1, f1 will be equal to v upon 2L, and this is called the fundamental frequency or first harmonic of a standing wave. So the first harmonic or fundamental frequency is the simplest mode of vibration in which string vibrate in one loop. Now second harmonic, which is also known as first overtone, when the string vibrates in two loop, it is called as its mode of vibration is known as a second harmonic or first overtone. So we know that the length of one loop is lambda by 2. So here length will be equal to lambda by 2 plus lambda by 2, since string is vibrating in two loop. So L is equal to lambda 2, or we know that same that f2 lambda 2 will be equal to v, and f2 will be equal to v upon lambda 2, or f2 will be equal to v upon L. Now I'm just going to find f2 in term of f1. For that I multiply the equation by 2 and divide it by 2. So v upon 2L is equal to f1, so f2 is equal to 2f1. The third harmonic or second overtones when the string vibrates in 3 loops, or we know that the length of one loop is lambda by 2. So L will be equal to lambda 3 upon 2 plus lambda 3 upon 2 plus lambda 3 upon 2, since there are 3 loops. So if we add them, L will be equal to 3 lambda 3 upon 2, or lambda 3 will be equal to 2L upon 3. Applying the same formula, f3 lambda 3 will be equal to V, or f3 will be equal to V upon lambda 3. Putting the value of lambda 3, f3 will be equal to 3V upon 2L. V upon 2L is equal to f1, so f3 will be equal to 3f1. So we can derive a general formula for the fundamental frequencies or harmonics. For that, I'm considering nth harmonic or n minus 1th overtone. So if the string is vibrating in n number of loops, we know that the length of one loop is lambda by 2. So L will be equal to n lambda n upon 2, or we can write it n lambda n is equal to 2L upon n, and frequency fn lambda n will be equal to V. So fn will be equal to V upon lambda n, or fn will be equal to nV upon 2L. So V upon 2L is the fundamental frequency, so fn is equal to nf1. So where f1 is the fundamental frequency, n is the number of harmonics, and fn is the harmonic frequency, or n will be equal to 1, 2, 3 up to so on. So if n is 1, fn will be equal to f1, which is fundamental frequency. If n is equal to 2, f2 will be equal to 2f1, which is first overtone, and so on. So the last topic for today's lecture is sonometer. Sonometer is used to verify the laws of vibration of a stretch string. It is the practical application of a stretch string for vibrating a portion of the string into desired number of loops. If we talk about the principle, it work on the principle of resonance. So what is resonance? When the frequency of the applied force is equal to the natural frequency of the body, the body vibrates with larger amplitude. So this is known as this phenomena is known as resonance. Now, construction. Sonometer consists of a thin metallic wire of 1 meter length, stretched across two bridges A and B on the top of hollow wooden block or box. Open end of the one end of the wire is fixed, while the other end passes over a frictionless pulley and is connected with a weighing pan. So this weighing pan produce tension in the wire or string. In between two bridges, there is a smooth movable bridge C. Slide over a scale to adjust the length of vibrating portion of the string. So here we have a diagram in which this is the wire of length 1 meter, and then this and these are the bridges A and B, and this is a paper rider or bridge C. So the one end of a string is connected with a rigid support, while other end is passing through a frictionless pulley and is connected with a weight. So in this sonometer, we use tuning fork to create or to apply frequency. If you are if you don't have tuning fork, you can use a vibrator. So the one end of a vibrator string is connected with vibrator, which continuously vibrate or the string, and then we have the formation of loops, and you can see that we have the string is vibrating in 3 loops, and then this is the amplitude, and the length of the loop string is L. So if we talk about the simplest mode of vibration, it is the frequency of vibration of a string is minimum when the mode of vibration is one, which is that when a string is vibrating in one loop, and the frequency is a fundamental frequency. So I have already derived the formula for fundamental frequency. It is equal to V upon 2L, where the speed of a transfer wave is V is equals to under root F upon mu. So this is the formula for the speed of transverse wave, and it is equal to the square root of ratio of force and linear density, where F is the force in Newton tension, and linear density is mass per unit length, mass of a string and per unit length of that string. So in this case, force is equal to tension, so velocity will be equal to under root t upon mu. Now if we put the value of v in equation, we have f1 will be equal to 1 upon 2l under root t upon mu. So in general, we can, if we are not talking about fundamental frequency, then it is fn which is equal to n f1, so n in upon 2l under root t upon mu, where n is the number of loops or number of harmonic or mode of vibration, and l is the length of that loop. So we have three laws of vibrations which we can verify using sonometer. The first one is Fn is proportional to 1 upon L, and it states that the frequency produced in a string for a given tension is inversely proportional to its length. The second one is Fn is proportional to under root t, and it states that the frequency produced in a string for a given length and material is directly proportional to square root of tension. And the last one is Fn is proportional to 1 upon under root mu, so it is the frequency produced in a string of some length and subjected to the same tension is inversely proportional to square root of linear density, and linear density is mass per unit length of a string. So this is all about standing waves. I have explained the equation represents the wave function of standing wave, and then using that equation I locate the points where the displacement is maximum or minimum. And after that the very important topic which is fundamental frequency and harmonics, and then at the end a sonometer. So in the end, I just want to say that knowing is not enough, we must apply. Willing is not enough, we must do. Thank you. If you have any question, please free to ask. I will try my best to answer it. God bless you. Take care.